Building on some of the concepts we learned when we talked about networks, our next topic is going to be the structures of silicates and also microporous solids like zeolites and MOFs. Silicates are far and away the most common minerals in the Earth's crust. They also represent a shockingly large number of known inorganic crystal structures. And this vast body of crystal structures shares many common features. Most silicates, the vast majority of them, contain silicon tetrahedrally coordinated by oxygen. And those tetrahedra, which are the building units of silicates, are connected together through corner sharing. So we don't see edge sharing or face sharing. Those two parameters alone mean that we can learn something useful when we think about the oxygen to silicon ratio in a given silicate. Now, before we do that, let's talk about something called the niggly formula. Here I've selected one silicate to illustrate how we can use the niggly formula to describe the bonding. This silicate is scandium 2 silicon 207, and so we might think about this as having scandium 3+ cations and then having this polyatomic silicon 207 6- anions. Now, if we look a little closer at the crystal structure, we see those polyatomic anions actually consist of two tetrahedra sharing one common vertex. Sometimes it's called a pyrosilicate ion. Now, the niggly formula for this anion is shown here. SiO 3 divided by 1 plus 1 divided by 2. So what does all this mean? We generally are going to have only one atom at the beginning. That's going to be typically the cation. That's at the center of the polyhedron. And then we have these fractions which represent the different kinds of anions in the polyhedron. So 3/1 means that there are 3 oxygens that belong only to one tetrahedron. Okay, we could call these terminal oxygens. And you can see in the picture here 1, 2, 3 oxygens which are not part of any other tetrahedron. They only bond to this silicon. And then we have 1 oxygen which is shared by 2 tetrahedra. That's our bridging oxygen here. Okay, so that's what the niggly formula tells us. Now, if we were to add up all of the numbers in the numerator here, we would get the coordination number of the silicon, 3 plus 1, 4, this tetrahedron. And if we were to add up the numbers in general, 3 plus 1/2, that would be silicon, oxygen, 3.5. Well, that gives us the correct ratio of the cation to the anion. And in Si207, there are indeed 3.5 oxygens for every silicon. Okay, knowing what we know about the niggly formula, then let's take a look at the oxygen to silicon ratio in a variety of silicates. When all of the corners of the tetrahedron are shared, as they are in the polymorphs of SiO2, then the niggly formula becomes SiO4 divided by 2. Right? And we have a 2-to-1 ratio of oxygen to silicons. When we see that ratio, we know that we have this 3-dimensional network of corner-connected tetrahedra. At the other extreme, if the silicon to oxygen ratio is 1:4, it means that none of the oxygen are shared. And so in this case, we're going to have isolated tetrahedra, which is what we see in the mineral zircon, zirconium SiO4. What can we learn from intermediate oxygen to silicon ratios? Well, if it's 2.5, that would correspond to 1 terminal oxygen and 3 bridging or shared oxygens. When you have that combination, the most common structural motif is going to be a 2-dimensional sheet of corner-connected tetrahedra. when you have an oxygen to silicon ratio of 3, that is 2 terminal oxygens and 2 bridging oxygens, there's a variety of structural motifs that can give you that, most notably an infinite one-dimensional chain or a ring of corner-connected tetrahedra. We'll see examples of both on the next slide. And when you have 3.5 oxygens for every silicon, that would be 3 terminal oxygens and 1 bridging oxygen. You have this dimers of corner-connected tetrahedra that we saw on the last slide. So visually, we can see some of these here. You can see in both images on the left-hand side that the 1:3 ratio does not uniquely tell you what the structural motif is going to be. We could have rings of varying size. Here we see a ring of 6 tetrahedra that we have in the mineral beryl. And that mineral, if you dope a little bit of chromium into it, gives you the gemstone emerald. But below, in sodium silicate, you can see we have the same ratio of silicon to oxygen, but here we have an infinite one-dimensional chain of corner-connected tetrahedra. In the upper right, this is just a portion of an infinite sheet of corner-connected silicon tetrahedra that you get in mica. And then down here in the bottom right, we see this pyrosilicate group, or this dimer of corner-connected tetrahedra that we saw in scandium silicate. Okay, if we were to focus a little bit on these three-dimensional structures that we can get with corner-connected tetrahedra, one very important class of those materials are the zeolites. So zeolites are framework materials that are built from corner-connected silicon and aluminum-centered tetrahedra. The word zeolite means boiling stone because when they were first discovered and people would heat them up, they would fizz and pop and boil because in these zeolites, as we'll see, oftentimes there are solvents like water that are trapped within the pores of the zeolite. The zeolites are an incredibly important class of materials for many applications. They're used for ion exchange. They're really important catalytic materials. For example, they're used in the cracking of petroleum to make gasoline. The ion exchange properties of zeolites find uses in, among other things, detergents. Zeolites are used as sieves, and they're also used to separate gases. So the list of applications of zeolites is quite long. Now, a related class of materials are called zeotypes, which have the same kinds of structures, but now they have elements other than aluminum and silicon on the tetrahedral sites. And then we have metal organic frameworks, which are coordination polymers that have open pores within them. And here we're largely using metal ions or clusters of metal ions that are coordinated by oftentimes multidentate organic polyatomic ligands. Now, we can classify porous materials as microporous, mesoporous, or macroporous depending on the size of the pores by which molecules can come in or out of the material. By and large, when we talk about zeolites and metal organic frameworks, we're talking about microporous materials. So let's talk about just a few important zeolites. I mean, this could be an entire course to itself, and later on in the textbook, I think it's chapter 14, is all about framework materials. Here we don't have time for that, but we'll just mention a couple of important ones. Let's start with sodalite, zeolite A, and phagosite. As we'll see later, sodalite is not actually porous, but it has the same kind of building block. All of these materials are built from this building block here, which is sometimes called a sodalite cage. We're going to take a closer look at that in a minute. In both sodalite and zeolite A, you have corner-connected aluminum and silicon tetrahedra. In these two materials, the ratio of aluminum to silicon is 1 to 1. So they're alternating silicon, aluminum, silicon, aluminum. Now, if it were all silicon, if this were silicon 12O24, we would have charge balance. But for every silicon that gets replaced by an aluminum, silicon is oxidation state 4, aluminum oxidation state 3. That means the framework now picks up a negative charge. And that's important because that negative charge is balanced by cations that go into the pores in the framework. Maybe it's a sodium. Oftentimes the cations come with waters of solvation. So you get these solvated cations that go into the pores. And that's really important because that's what creates the pores. If you didn't have to have the cations around for counterbalance, you would more than likely form a dense silicate, not a porous one. We're not going to deal here with the cations or what's going on within the pores. We're just going to talk about the frameworks, but that's an important thing to know. The other things that we see here, we can see the size of the ring. We'll say a little bit more about that later on. And we can also see how much of the volume is porous, that is accessible. So if we were to take a 2.8 angstrom diameter sphere and move it around within the solid, the question is how much volume could that sphere access? And so in zeolites like zeolite A and phagosite, it's about 25% of the volume. And then another critical thing is how big are the openings by which molecules or guest species can come into and out of the porous material. Because if these are not large enough, it doesn't matter how much volume there is on the inside, we can't access it. So let's take a little bit closer look at this sodalite cage, which is the key building block of these three very important zeolites. Okay, to do so, let's go back to our lecture on nets. Remember when we talked about uninodal four-connected nets? We talked about the diamond network, which is the most symmetric four-connected net. So in diamond, all of the vertices have perfect tetrahedral symmetry. We also talked about Sodalite, which is also a four-connected net based on tetrahedral vertices, but the symmetry is actually hexagonal, so it's not quite the same high symmetry as diamond. There are other four-connected nets that we did not talk about, quartz being an important one, but in the context of zeolites, a really important four-connected net that's quite symmetric is the Sodalite net. So that's shown here. So if you look at any of these vertices, you would see that they are four-connected, and it is in the shape that's quite close to a tetrahedron. And here are some of the details. We see that the site symmetry is not a perfect tetrahedron. It's 4-bar M2 or D2D, but that is still quite high symmetry. In fact, that's a higher symmetry vertex than we saw in Sodalite. So what's the relationship between this network and sodalite cage that we see in a zeolite? That network takes its name from the mineral sodalite, which I show here. Sodium, aluminum, silicon, oxygen, chlorine. Maybe you can see these blue looking vaguely like a soccer ball. Probably the best way to describe that blue cage is it would be a truncated octahedron. And in that blue object, we can see that we have hexagonal faces. And so if we were to go around there, that would be what we call a 6 ring. And then we have these square or diamond faces, which are made up of 4 atoms. So we could call those a 4 ring. That cage should look very familiar to you because it's exactly like the topology of the sodalite net we saw on the last slide. Now, in this structure, we also have chloride ions that go in the center of these cages, and we're not showing the sodium nor the oxygen here. All right, so you can see that that is the building unit of many zeolites. In sodalite itself, the cages are fused together in such a way that it's not really porous. There isn't really a way for molecules to go in and out of this structure. If we were to look at just a single sodalite cage and think about some of the ways we built up structures from nets, I mean, here what we want to do is we want to, first of all, we want to apply site ordering to get a homeotype. And by that, I mean we alternate from aluminum, silicon, aluminum, silicon, aluminum, silicon. Right? So all of the vertices have been ordered. And then the other thing is now let's bring the oxygens in. All right? The aluminum and the silicon are not making a bond to each other. There's an oxygen in between them that's holding them together. That is the vertex of the tetrahedron. It's worth pointing out that the oxygen doesn't sit right on this edge. If it did, that would be a linear 180-degree bond angle from aluminum to oxygen to silicon. Instead, that angle is about 145. So even though the oxygen isn't on the edge, we do still have a perfect network of the tetrahedral aluminum and silicon atoms. We could look at the sodalite cage in a variety of ways. Here is another view from chapter 14 of the textbook. And in this image, we're not distinguishing between aluminum and silicon, but you can see the corner-connected tetrahedra. You can see that there is open space within that cage. Here's a polyhedral view. Here's another view where we just connect the vertices by a line. That's kind of like the network view. And then the view on the far right is where we are drawing the oxygens at their proper radius. And when you look at it that way, you can see that, in fact, this is not really porous. There's no real space big enough for molecules to get in and out. I think this space right here is about 2.5 angstroms by, maybe 1.5 angstroms. That's just not big enough for any molecules to go in and out. So how do we take that sodalite cage, which is hollow in the middle of it, and make a porous material? And the way that we're going to do that is we're going to not fuse the sodalite cages together so they share a common ring, but we are going to connect them through an oxygen bridge. So if we have another linker here, an oxygen that links from this silicon to another cage, so we'd have silicon, oxygen, silicon, and we connect them through the diamond-shaped 4 rings, then we're going to get a material called zeolite A, right? And this you might think of as a primitive cubic network of sodalite cages. And these rings, I believe, are 8 tetrahedra around, and they have a pore diameter of about 4 angstroms. So now that's big enough for small molecules to move in and out, for ions to move in and out, for solvent to move in and out. If we link the sodalite cages not through the diamond or square 4 rings, but instead through the hexagonal faces, then we get this zeolite that's called phagosite. And now we have an even bigger opening. And the pore diameter now, the available space for a molecule to squeeze in and out is 7.4 angstrom. You can get moderately large molecules in and out of these openings to access the available space within the zeolite. If we were to think about this structure as having a sodalite cage on each vertex of a network, and those sodalite cages are then linked by the oxygens, this network would actually be the diamond structure. So this is like a supermolecular assembly of the diamond structure with a sodalite cage at each vertex. Now, MOFs is an entire field. I know there's some people here in the class who are working on metal organic frameworks or covalent organic frameworks, and those are really interesting materials. I don't really have time in this class to do it justice. Let me just talk you through one of the most important MOFs, a MOF called MOF 5, and how we can think about that structure as being constructed from one of these nets. So we're going to start with a simple cubic net, and then at each vertex, what we're going to do is we're going to put an oxygen atom. And then around that oxygen atom, we're going to put 4 zinc cations. All right, so we're going to decorate the lattice point with an oxygen zinc 4 cluster. Then we're going to link together the vertices, these OZN4 clusters, with this benzene dicarboxylic acid linker. So you've got a benzene ring, and then on either end, a deprotonated carboxylic acid group. So the oxygens of the dicarboxylate group can also coordinate the zinc. You can see that better up here. And we end up with zinc that's in a tetrahedral coordination. All right, so we decorate the vertices, and then we expand the lattice through these extended linkers. And that gives us MOF 5. And there's actually a whole series of MOFs where we make the linker bigger and bigger, and that gives us more and more pore space. At some point, when the void space between the linkers gets big enough, you end up with problems of MOFs that are interpenetrating. So you have one MOF interpenetrating through another one. And that's something, if you're into MOF chemistry, you've got to do certain things to avoid that. The reference I give here at the bottom is, I think, an interesting paper to think about the relationships between these MOF framework structures and a lot of the inorganic crystal structures we've already been talking about.